In 2012, a professor at UCSD was pulled over for purportedly rolling a stop sign. He was able to apply calculus in order to defend his position that he indeed made a full stop. He makes the claim that the officer was judging him by his angular velocity rather than linear velocity, making it seem like there was acceleration at the stop sign. And a brief obstruction with another car in the adjacent lane made it difficult to see whether he stopped completely. This diagram shows the geometry of the considered case. Car C moves along line L. Its current linear speed is v, and the current distance from stop sign S is x. Another road connects L perpendicularly at S. Police officer O is located on that road at distance r sub 0 from the intersection. The angle between OC and OS is alpha. Through using the diagram as a reference, we can assume for a moment that C's linear velocity is constant in time t. We can also choose time units t such that t equals 0 corresponds to the moment when C is at S, and find distance x. Then observer O visually measures not the linear speed of C, but its angular speed given by the first derivative of angle alpha with respect to time t. To express alpha of t in terms of r sub 0 and x of t, we can use a standard trig equation making a right triangle using the diagram that I used earlier. And then we can substitute this equation back into the previous equation and use standard differentiation rules, where f of t is any function of t, but it is f of t equals v sub 0 times time over r sub 0. Here we find that the angular speed of C that O observes as a function of time is this equation. A graphical representation of this function shows that the visual angular speed of C moving at a constant linear speed is not constant. It is the higher, closer C to O, and it goes over a sharp maximum at t equals 0. We also have to consider that the car came to a complete stop using linear deceleration and acceleration. Therefore, distance equation is going to be different. And using this distance equation, we can actually derive the velocity equation and use the definition of the velocity in order to find the angular velocity that C that O observes. The graph of this function now shows that there is a complete stop at t equals 0 based on all three of these possible times where it decelerates and immediately accelerates after t equals 0. Finally, we need to consider what happens if the police officer's observations are briefly obstructed by another car. The professor's car was driving a Toyota Yaris, which is about 150 inches, while the car that was obstructing the view was 189 inches. To estimate times TP and TF at which the partial and respectively full obstructions of views of both cars began and ended, we have to use the equation substituting x of p equals L2 plus L1, which equals 8.16 meters. X sub f can be seen as L2 minus L1, which equals around 0.99 meters. Using the previous x distance equation, we can solve for t in order to find the partial and full times of obstruction and get these two values, 1.131 seconds and 0.45 seconds. Finally, we were interested in finding t prime at which the angular speed of the professor's car observed by the police officers without any obstructions goes over its maxima. The easiest way to find t prime is to recall that the value of the first derivative of the angular speed at t prime is 0. And then we just differentiate the equation of angular velocity that we found earlier, and we need to know that the function is 0 only when the numerator is 0, so we take the root of the top of the equation and find that the value of t prime equals 1.07 seconds, which means that t prime lies between the full and partial time, meaning that the times are actually really small. In summary, the police officer made a mistake according to the professor, confusing the real space-time trajectory of his car, which moved at approximately constant linear deceleration, came to a complete stop at the stop sign, and then started moving again with the same acceleration.